All right, so, okay, real quick, how do I tell if two vectors are orthogonal to each other? Take the dot product and do what happens? 0, yeah. So for problem 1, you just need to check that the dot product of u and v is 0, which will hold exactly when u and v are orthogonal to each other. Right? 2. Okay, now this is probably the one that I was curious if people had this formula in mind. It says find vector projection of u onto v. So the picture here is you have some vector u and you've got some vector v, and you're trying to figure out what this vector right here is, right? This vector is called the projection of u onto v. So whether memorized or not, whether you're getting it from the geometry, the basic idea here is that the computational formula for projection, which is something that you should know, I covered this in the video on this section, the projection of u onto v is u dotted with v over the length of v times v over the length of v. That's the way I like to remember it. The constant has to do with turning v into a unit vector and dotting it with u. That gives you the length. And then you multiply it by a unit vector pointing in the same direction as v. The way most people remember it is u dot v over the length of v squared times v. Either way. It's important to use v here and not u because we're projecting onto v. So the vector that comes out at the end when we're projecting onto v has to point in the same direction as v, and that's what the v is doing here. Right? It's easy to get that backwards, so be careful with it. This quantity, so like, I don't know why, I have no idea why the book uses the notation comp for this, but the scalar projection, we're going to be using this today. The scalar projection of u onto v was a number, and you get that by doing u dot v over v. Okay, it just tells you how many copies of how many copies of this of a unit vector in the direction v you need to get. Okay, finally for question 3, it says compute a vector orthogonal to two vectors, which is basically screaming out for a computation of a cross product, right? U cross v is orthogonal to u, and u cross v is orthogonal to v. When you get asked to produce a vector orthogonal to two other vectors, you take the cross product. The cross product of u and v, or v cross u, it does not matter because both vectors will be orthogonal, just pointing in opposite directions, is the determinant of the matrix I, K, A, U1, U2, U3, V1, V2, where we use the determinant computation to produce it. When you're finished, when you're doing a problem like this and you've produced something as a cross product, it's always a good idea to go back and actually dot it with the original vectors and make sure that the thing you've got is actually orthogonal. Because if it's not, it's messed up. Okay, so that's the game behind 3 there. So I'll post solutions to these when I sit down. Later. Any questions on it yet? Okay, so everything here are basic computational techniques that you're essentially going to need in every class going forward that involves like modeling things in multiple dimensions. So you've got to have these in your head: dot, cross, products, and these projection formulas come up over and over again. All right, so the first thing I want to do today is I'm going to talk about this problem. This is the last part of 12.5, and then we'll move on to 13.1. So one awesome thing that vectors get you is computational formulas that are not available to you in any other context. The question says, the big question that this fits into, right? The type of question it fits into is called distance between and a plane. So the picture that we're looking at here is this. I've got some plane. I'll call it, I don't know, P. That seems a reasonable name for a plane. Maybe not. Maybe P will be point. We'll call this L. And then there's a point floating up here, P. And by the distance from the point to the plane, I mean, if I took a straight down direction, so I was perpendicular to the plane, what's the length of this right here? So the length of this line that goes from here to here, where this is at a right angle to the plane, is called the orthogonal distance. Usually we just even leave off the word distance. It's the closest I can get to the plane with a line segment. I mean, I can connect that point to the plane with lots of different line segments, but there's one unique one that makes that as small as possible, and that's what we call the distance. So if you've seen this question before in earlier contexts, what you do is you write down the distance formula, and you have some point running around inside the plane in terms of x, y, and z, and then you've got to take a derivative and maximize and minimize it. That sucks. It's a terrible way to do the problem. It works, but I mean, you can do this. You can set this up. So the Calc 2 approach. Is to say, oh, well, the distance formula is a function. I can take its derivative, and I can find the minimum of that. Right? Find a minimum value, and that will tell me what the distance is. You minimize distance formula. Derivative. That's kind of awful. A lot of machinery there. There's square roots running all over the place, right? It's not a fun way to compute this exercise. I want to point out as well that finding minimum distances between things is the core idea of an entire type of computational math and science called optimization. You have a solution set, and you want to find the best one, which means one way of thinking about this is, well, this is what my model spit out, but the closest good answer in my good space is the one that's like the closest. I mean, data science is built out of this idea. Convex optimization is built out of this idea. Finding the closest distance between two things. So this is a live question, right? This technique here, and this is the approach. It's kind of ugly. So what we're going to do instead is we're going to try to reformulate this question by thinking about vectors. So I'm going to redraw that same picture, but I'm thinking of everything as vectors instead. Pick any point in the plane you want. Any point. So we will call that P0. Those are usually easy to read off because, for example, here, can I come up with a quick point that's inside this plane? It's any x, y, and z that satisfies this equation. They're an obvious one. What's your favorite? I had one earlier. Find me an x, y, and z that satisfies this. 1, 1, 1. 1, 1, 1. Well, that would give me 2 plus 3 plus 4, which is 9 is equal to 1. That's a false equation, so it's not in the plane. I have to have a. What's that? Okay, never mind. You are correct. The way I've written it, it does look like a minus. It says, never mind. I take back my incorrect statement. Okay, so if x is equal to 1 and y is equal to 1 and z is equal to 1, you get 2 plus 3 minus 4, which equals 1. 1 is equal to 1, so we're good, right? The fact that these numbers go in here and satisfy this means that this point is in the plane. Okay. So that point is 1, 1, 1. Now I've got some other points. 2, 2, 2, which is floating out here somewhere. And then what I'm looking for is the orthogonal projection of this point down onto the plane, right? This point right here, that's the one I want, it's right there. Except I don't even, do I need the point? Do I need to find that, or do I just need to know how long this piece is? Just how long, right? I mean, the distance is just the length of this. So this, I want this distance. I want the length of this. So we're going to vectorize this picture by saying, okay, I know a vector that points in that direction. A vector that points in the same direction as this vector right here is the normal vector n, because n is also orthogonal to the plane. So I can think about this line segment as living inside the normal vector to the plane, right? It's in the same direction as the normal vector. Make sense? Okay. So what I'm going to try to do is draw a triangle and use vector projections here. Because I think if I could draw this vector, and then I could project this vector onto this one, the length of the vector projection would be the same as the distance between this point and the plane. And I'd never need to find that point. The calculus way, you find the point first. We're not finding the point. We're just going to calculate the length of this little vector. So my claim is that if you look at this right here, which in this case is also the vector 1, 1, 1, the vector that connects this point that I know is in the plane to the point I'm trying to figure out how far away it is, and I compute the projection of that vector onto the normal vector, we'll use the book notation here, comp, which just means scalar projection. Because I don't care about the vector, I only care about the length, right? And the length of this vector is going to be equal to this computation. Make sense? Notice no calculus, no optimization, just projection. Do I know n? Damn, I'm stuck. What's n? For this plane. Well, do I have a plane written down somewhere in terms of an equation? We use it to produce the point. That's the equation of a plane. What's the normal vector? I'll remind you. When you're looking at a plane, you have 4 different ways of writing the equation down. N dotted with r minus r naught is equal to 0, or x minus x naught times a plus b times y minus y naught plus c times z minus z naught is equal to 0, where n is equal to a, b, c, r is equal to x, y, z, r naught is x naught, y naught, z naught, or ax plus by plus cz is equal to d, where the normal vector is a, b, c. 3 different formulations for the equation of a plane: the vector form, the sort of point slope form, and the linear form. What's the normal vector? 2, 3, -4. -4. A, B, and C. The numbers attached to the X and the Y and the Z. So we're projecting. This is dead easy to compute. Now I'm going to warn you about the way the book approaches these questions. What the book says is memorize this huge, awful formula. That's what it, that's what it gives you, right? If you look at the top of page, if you look in your book and you look up at the top of page 870, there's some crazy formula that comes out of this projection, but you don't need to know it. You don't need to memorize it. You just need to know this picture. The picture that you memorize here is that all you're doing is finding this vector and projecting it onto the normal vector. So yeah. So this is an argument for the elegance of the vector approach, right? That we've completely removed optimization and calculus from the picture, and instead we're just using projection to think about the answer to this instead. So the picture without any numbers put into it is you have some point r naught, you have some point p, you compute the vector p minus r naught, you've got a normal vector n, right, this is n, and then you just compute the projection of p minus r naught onto the normal vector. This vector projected onto that one. All right. I guess we could finish the question, I suppose. So in this particular problem, what we're computing is 1, 1, 1 dotted with 2, 3, minus 4 over the length of 2, 3, minus 4, which is 2 plus 3 minus 4 divided by, okay, the square root of 2 squared plus 3 squared minus 4. And for me, that would be sufficient. You don't need to compute any further than this. But this expression right here is the formula that teach you to memorize in the book. I don't want you to memorize the formula for that. I want you to think about this picture. Okay. This is a trick, by the way, that'll save you sometimes in physics classes. You think about things as vector projections. All right. And I promise you that won't be the only time in your life you see that formula. All right, so are there questions about anything from chapter 12 before we go on to chapter 13? Anything I can answer? We can start doing calculus again. Cool. I'm going to reiterate before I erase this. This picture is important. This vector right here, the length equal to scalar projection minus r naught. Okay, so let's talk about vector functions. So a vector valued function is a function r of t that in 3 dimensions anyway, all that means is that you have an f of t producing the x coordinate, a g of t producing the y coordinate, and an h of t producing the z coordinate. Now you might look at that and say, how is that any different than a parametric equation? And the answer is, it's not. It's just conveniently encoded in vector form. Okay. This is in 3 variables. And then oftentimes we also are interested in working in 2 variables, in which case there is just a function keeping track of where x goes and a function keeping track of where y goes. So a typical example of something like this might look like r of t is equal to cosine t sine t, and suppose I let t be in the interval from 0 to pi. Here's a vector function. That can be a function. It takes in a real number. It spits out a vector. Now, of course, you can parameterize this if you want. This is equivalent to the equation x is equal to cosine of t, y is equal to sine t. The reason we did parametric equations is because you can think about vector equations as parametric equations. So what is the graph of this vector function when you trace it out? You guys remember what cosine t sine t is? Yeah, well, half of it because I've only gone from 0 to pi. R of t is equal to cosine t sine t. We think of as being this set of points. So the reason that we're thinking about it as vectors here the reason that we're thinking about this as vectors is we imagine that what's happening is that there's a vector arrow pointing out to the end, and the curve that you get is where the tips of each of those arrows is. So the tips of these vectors sweep out this curve that we're plotting. That's the way we think about this. We're plotting it. And we really want to think about these as vectors because if there's a vector at this point, I can think about a perpendicular vector to that vector at the same point, right? Why we're going to be doing this with calculus, you might think, why does it make any difference to think about these as arrows pointing out here? And the answer is, if I have an arrow, arrows have a very natural idea of orthogonal vectors attached to those vectors, right? That doesn't necessarily rely on the existence of a derivative. This is going to allow us to mix vector geometry together with derivatives. That's kind of why we're thinking about these arrows connecting out to the curve. So we can use dot products when we start talking about derivatives. Okay, now these, one of the more, I'm going to say what math professors enjoy doing with these things is drawing them. And of course, if we like drawing them, then we like you to draw them too. So for example, one classic here is R of t is equal to cosine t sine t. Just let t be any real number. The domain of, say the domain, everything from minus infinity to infinity. What are we looking at? There's some art into learning how to tackle drawing these things. So I'm going to point out at the beginning, it looks easy when your professors draw these things on the board because we have a lot of practice. Right? So does anybody want to take a stab at what this looks like without looking at the book? There's a picture of it in the book. Like, what are these guys doing here? The x and the y coordinates, what are they doing? It's cosine and sine, right? So they're just going around in a circle. X and y are just going around and around and around in a circle. So, okay, this is a good idea. So I've got cylinder, I've got coil, plane, so stuck in a circle in a plane. A sphere, okay, that's a good one. So I've got 4 reasonable guesses as to what's going on with this function. So the cylinder idea, that's a good place to start. So x and y always have to be on the circle of radius 1 because cosines, I mean, they have to be. This is a unit circle in x and y, right? So I'm going to try to draw this in 3D here. So there's a circle here. And living above that circle is some cylinder. And whatever is going on in the z variable, so z is in this direction. Whatever's going on in the z variable, the x and the y must just be doing this. They're going around and around and around like this, because that's all this can do. If there was no z here, that would be a circle. But what is the z coordinate doing? As t goes to infinity, what is the z doing? It still goes to infinity, right? Z must be going somewhere because the z coordinate moves. So the x and y coordinates are going, and you can probably just imagine visually. I'm trying to connect a visualization of what's happening here. And not so much like, you can plot points, but it's easier if you try to figure out exactly what's happening with it. You have an x and a y coordinate that are spinning in a circle forever. But as t increases, the z coordinates are going up. So what you get is a shape that looks like this. Around back, and then it comes across the front, and around back, and across the front. I'll draw it like this. So it goes up and around the back, and across the front, and around the back, and across the front, and around the back, and across the front. What you get out is called a helix. So already with vector equations, you end up with these sort of shapes that you don't get in 2 dimensions, right? Like these, I mean, this is still kind of like a graph because it's built out of something that looks like a line, but it's twisting through space because of the way we set this up. Okay. And so that's the sort of shape that we're going to be. It's stuck in, yeah, so it's climbing up the z-axis, but it's stuck inside the cylinder. It's stuck in the cylinder because the x and the y are always on that same circle. What's happening is as the z increases, it twists around and around with the z-axis in the middle.
So it doesn't always touch the line.
What do you mean? Does it touch the line that's?
Part of
So this is kind of a good picture of it might look like this. I'm going to exaggerate it. So this is the cylinder that x squared plus y squared is equal to 1. It's like the unit circle, right? And the z-axis kind of goes up through the middle of this, yeah? Does that make sense to you? Okay, so what is the helix doing? Well, it's just a curve, it's just a line, and it has to stay on the outside of the cylinder because that's where it lives, right? X squared plus y squared is 1, so it's stuck on the circle. So as the z coordinate increases, this is where as z goes up, it means to go this way, right? 0 is down here, infinity is up here. So to go up in the z coordinate means to travel like this. So you kind of get a shape, and without reference to a coordinate system, what's happening is it kind of goes up, and then it crawls around the back of the cylinder, and then it comes around the front, and then it goes around the back of the cylinder, and then it comes around the front like that, but forever. It's coiled like a barber's pole. You guys know what I'm talking about, right? So coiling up forever. So now what's the calculus here? Why do we care about, like, let me give an idea of like, what are the sort of questions we're going to be asking about? What shapes like this? The first thing is, I would like to be able to describe things like, if I think about this as a path of a particle, I mean, I can imagine that what this is there's some particle where this is describing where the position of the particle is. I might want to know how fast it's moving, right? Well, there's a connection with physics here where the velocity with which the particle is making this path happen, or is traveling on this path, is contained in here inside of a derivative. So velocity is going to be present here. Distance traveled is going to be present in here as well, because the arc length of pieces of this will tell you how far something moved. So there's these live questions that we have about how we can translate ideas from regular old 2-dimensional calculus to this setting. We really want to know about stuff like, velocity, which really means knowing about tangent lines. Remember, velocity in a physical setting comes from a derivative, right? Velocity is derivative of position. But here, I don't have a number. I've got vectors that poke out. So how do I make that make sense? If velocity if I take a derivative in this context, I'm going to get vectors out. And I got to work out how to deal with that. I'm also going to want to have questions about arc length. How far a particle is gone. And then the last thing we'll deal with in this chapter, none of this is stuff we're going to do today. I'm just going to give you an idea of where we're going, right? The last thing is that there's another idea associated with this that has never come up in any context you've seen before, probably, which is the idea of twisting is possible, right? So in a mathematical sense, this is where torsion shows up for the first time in math. Probably some of you were in engineering classes where you computed torsion, or physics classes where you computed torsion. The way you can think about it is, there's some sense in which this path is twisting around as it goes. And we're going to come up with a mathematics that's going to describe, if you were on this, what would it feel like as you twisted along the path as you went up? Okay. And that's going to involve not only the speed with which you're traveling, but also how tight the corner you're taking is. So there's also notions in here of ideas that we haven't really dealt with about curvature. So curvature is going to turn out to be a measure of how tight corners are. Imagine a car taking a gentle turn, you feel less force than you would if you take a tight turn, right? That's related to something that has to do with derivatives here that we can measure with calculus. Vector functions are useful precisely for this reason, because it gives us a way of describing physical forces in 3 dimensions. This is why all this math was invented in the first place. So I guess I should point out some basic properties of these sort of maps, which is, here's the nicest one. The limit as t goes to a of a vector function r of t, you could just put the limit inside. That's easy. That's the same as saying the limit as t goes to a of f of t with the h of t. And I can just rewrite that as compute the limit of the first part, compute the limit of the second part, compute the limit of the third part. So limits are just taken what's called entry or component wise. Limits apply entry wise. We also have a very natural notion of continuity. Once you have this definition, you can say R of t is continuous at t is equal to a if the limit as t goes to a of r of t is equal to r of a. If the function looks like it's going where it actually is going, the function is continuous. This is the same definition of continuity from calculus 1. The reason we need continuity is because we can't even begin to deal with differentiability unless we've got a notion of continuity. Okay. So some basic exercises that you might get in the basic language of vector functions might look something like find the limit. The book is going to enjoy taking this opportunity to ask you guys things that it's trying to remind you of that you're supposed to know. So you might get asked something like, find the limit as t goes to 0 of sine t over t, cosine t, natural log, no, it's not natural log. Yeah, natural log of t plus 2. Can't get intimidated by this because it's no different than just computing 3 limits independently. And the reason I say that books like to use this to sneak old knowledge back in is because it might ask you to remember things like what is the limit as t goes to 0 of sine t over t, which is the engineer's limit, right? 1. You evaluate this limit, which is 1. You evaluate this limit, which is cosine of 0. Or if you're lazy, cosine of 0. And the natural log of 2. Evaluate each piece independently. Okay, limits are evaluated in a natural way. This is actually the advantage of thinking of this. So, a common sort of response to learning about vector notation is to think this is no different than parametric equations. Why are we doing it this way? But notice I can do it all at once. I don't have 3 different things I'm computing. I have one unified function I'm working with. Okay. And let's see, other than that, it's just amusing exercises and things like this. I think they're amusing anyway. Okay, so I could ask you something like plot R of t equal to a very really there's that one, that's no fun. Okay, what if I told you to plot R of t is equal to Sine t. It's a two-dimensional plot, not a three-dimensional plot. You should just be able to do this in regular old two-dimensional coordinate system, right? The easiest approach you can take to something like this is to think, what is the relationship between the x and the y that you're being asked to solve here, right? So when I look at this, I think, okay, well, it's telling me that my y is equal to t and that my x is equal to sine of t. But we already know, so this is called a, so we were looking at the parametrized equations. Notice that throws away the idea that there's some particle moving, and it just, if we're going to eliminate the parameter, we're going from a moving particle to just the path that it took. This describes the position of a moving particle. This, if we eliminate the parameter, will just tell us what path it took. So if you eliminate this parameter, well, since y is equal to t, you can write x is equal to sine y. This is just the path. There's no notion of motion here. We've lost the idea that something is moving. But if we're just trying to draw the path, this is a good place to do it. How do I draw x is equal to sine y? Don't think too hard about this. Just tip it up, right? I mean, it's sine, but tipped up on this axis instead. So there you go. X is equal to sine y. Now notice though, while this does give me a plot of the path that this function follows, it doesn't tell me anything about where it's moving or how quickly it's moving, right? I've lost the idea of parametrization here. If I plug a particular point in, like t is equal to 0, I'd have to go figure out where that was by looking at this equation. So r of 0 is equal to sine of 0, 0, which is 0, 0. So that point right there corresponds to t equals 0. T is equal to pi over 2. That would be the point sine of pi over 2, pi over 2, which is 1 pi over 2, which is this point right here. And there's a notion of motion here where the particle is traveling this way along the path. Right? That's the basic idea. These are the sorts of curves we're going to be studying with the derivative. Because again, I could ask the question, how fast is the particle moving? What velocity is it undertaking to move? Right? How far does it travel? And all that are questions that are going to involve looking at the derivative. So in 13.1, the basic exercise is going to be to plot simple space curves like this. Okay? All right. Next time on Monday, I will describe what the exam is going to be like. We'll do a pretty thorough description of the topics that are required. And then my feeling is that I probably am going to be able to talk about a little bit of 3.2, at least up to the computation of derivatives. Okay. So 13.1, 12.5, 13.1, and 13.2 will be up this weekend, but the only homework that's due prior to the exam will be 13.1, I believe. Right? Or the latest, the last one. We'll talk about it on Monday. Have a good weekend, guys. Yep.